Oh, is it coffee?
Mm-hmm.
Thank you. Okay. All right. Good. Great. Let's wait a minute for people to come back on. Where were we in the set when you got cut off, or I got cut off, or my kids started running BitTorrents to download movies illegally from China or something? $19, $18. Okay, so I'm not sure where we were. I'll just restart maybe from it was just the last three, maybe 18. No, it couldn't have been 18 because we already did that one. That was the one that Eric asked about, last one, and then maybe the last two got cut off. So I'll do 19 and okay, so there we go. Good. So let's come back to that's 18, at least on my set. There was scramble for you guys. And we decided that first of all, the answers were certainly screwed up. So those don't work. But interesting problem, kind of, because looking for magnetic flux, a magnetic field equals 0. Wait, so D was correct for the concentric hollow spheres. Excellent question. So there's clearly confusion. These are not spheres. It's an end view of two cylindrical, good. Thank you, Hannah. Yes, so these are basically currents that's kind of flowing like this, and then inside, like in a shell, like that, and then that way. And if we do the Amperian loops, I've got those drawn in at 3 spots, and I didn't put in a 4th spot, which is the trick. So in the red loop, of course, inside that we have no current, so magnetic field is 0 everywhere for little r, small r, big R. Everywhere for between R, big R, and 3R, actually, we have inside that location a current into the paper, and therefore the magnetic field will be clockwise. That once we get outside the outer shell, then the magnetic field created by the outer shell will overwhelm that magnitude of the magnetic field created by the inner shell, because there's more current flowing through the outer shell because its cross-sectional area is bigger. They have the same thickness, but the circumference is bigger. So more current flows through the outer shell. Therefore, if we go outside the entire assembly, then because the outer shell has its current coming towards us, it does, that means the magnetic field would be counterclockwise, outside the whole thing. But between points, between the 3R and 4R, there is a point where the current inside that Amperian loop would be 0. So, because you basically just make sure you push that radius far enough out in order to get just enough current on the outside as there is in the inside, and then that radius, there would be no magnetic field. And the answer they have is D, so that makes sense. So they lost a, there's like a, anyway, I don't know how that's, I can find, maybe I can find the original question. I'm not sure what got modified. Anywho, so 2 more questions on this set. Yeah, so D makes sense, even though the way they, I would have liked to have somewhere between 3R and 4R or something like that, but it doesn't say that, so I'm not sure. Yeah. Anyway, okay, so back to this, the next one. Next one we have is relatively straightforward, I hope. We have 2 currents at right angles. They don't touch, obviously, that don't work. So looking at this, the situation, the current creates magnetic field at the point, and you might be worried about them being not in the same direction, but they are at that location. They are in the same direction. So they add straight up at that point. So if your upward current has a value of B and the horizontal component wire has a magnitude B, you would now be at 2B. Now, on the other hand, if we double one of the currents, then instead of producing B, that wire will produce 2B at that location. So 2B plus B is 3B. So now we have 3B compared to 2B. So it's increased by 50%, or it is 3/2 of the previous value. All right. So here we go. This is a loop with a current flowing, and we're asking for the net force on that loop by the straight wire, which is beneath it. The magnetic field created by the straight wire at the bottom will be strongest near it because it's inversely proportional to distance, and then it drops off as you go further away. I signified that by having the big X's on that lower wire on the loop, and the upper wire has it as a smaller X's. That's not a technical way of showing them. I just kind of showed it that way. The big X's, big magnetic field, mean big force on the bottom wire compared to the top wire. Directions are opposite because the currents are flowing opposite directions. The side wires have the same current and average the same distance, so they will add up to 0 force because the forces are opposite and equal to each other, not according to Newton's third law, though. Okay, and that is that. Okay, that's the 20 questions on the quiz. I saved the other first part of this live stream, and we'll save this as well on my channel. And we're at the end of the hour that I said we'd do, which is fine. And here is maybe a chance. I have 5 people left here. Maybe some feedback, whether this is good, bad, terrible, helpful, mixture of things. How should we move forward in terms of continuing our work? I've already posted 3 videos for you on the next Unit 5. As you know, I think I've assigned problems as well. And we're still aiming to do the quiz day 4 before Easter vacation. So class during Easter vacation, the actual spring break. So that's kind of the last day of school is April 3rd. And I had the quiz scheduled for the 2nd. This was helpful. Thank you. Okay. Yeah, you're welcome. Happy to do it. So we'll do some of this and some of the other things we've done. I'm glad that technologically I can do this from home, apparently better than from, I'm not glad about that, but I'm glad I can do it actually. Okay. All right, well, you guys don't have to comment right away. I'm just gonna sign off, and then maybe if you guys wanna put some feedback into the WhatsApp group about this process and suggestions for improvement and all that, and then we'll go from there. All right, au revoir. Like my little American accent on the French there.